Hello friends, let us solve another important problem on the effect of undersampling, which is aliasing. But before we look at the problem, let us try and understand the important difference between the continuous time frequency variable and the discrete time frequency variable. Let's say we have a continuous time signal given by x subscript a of t equal to a cos omega t, where omega is the frequency in radians per second. This can also be written as a cos 2 pi f e, where this capital F is the frequency in hertz or cycles per second. Now, if we sample this continuous time signal, this is a continuous time signal. If we sample the signal uniformly at a rate with sampling interval Ts, then we can write the sampled version as Xa of nTs, and for convenience we denote this as x of n equal to a cos 2 pi f, and we replace this small t by n times ts, where ts is the sampling interval and 1 by ts, which we denote by fs, is the sampling frequency. Now with this we can write x of n equal to a cos 2 pi f, and for this ts we write 1 by fs, so 2 pi f by fs into n, and now this f by fs is the ratio of two frequencies which we denote by lowercase f. So this is equal to a cos 2 pi small f n, and 2 pi small f we denote by small omega, so a cos omega n. So given a continuous time signal xat equal to a cos omega t, we obtain the corresponding discrete time version of the signal, which is a cos omega n. So it looks similar in the form, but there are some major differences, and we need to understand that this capital omega is a physical frequency in radians per second, and the capital F is corresponding frequency in hertz, physical frequency. However, small f is the ratio of two frequencies f by fs, and therefore it's a dimensionless quantity. It is the normalized frequency. So note that this capital F can take any value up to infinity. If we consider negative frequencies as well, we write capital F lies in the interval from minus infinity to plus infinity. Accordingly, capital omega also, which is just 2 pi times capital F, lies in the interval minus infinity to plus infinity. On the other hand, small f, which is just a number ratio of two frequencies, it cannot take any value. As per sampling theorem, the sampling frequency fs must be greater than or equal to twice the maximum frequency of the signal, which is f in this case. So it must be greater than or equal to 2f. From there, f by fs must be less than or equal to half. Considering the negative frequencies, the interval is from minus half to half. And for lowercase omega, accordingly, which is 2 pi f, if we multiply by 2 pi on both sides, we get minus pi to plus pi. So this difference is very important to understand, that the continuous time frequency variable denotes the physical frequency in radians per second. However, the discrete time frequency variable is a normalized frequency. It is not the physical frequency, the absolute frequency. And to know the corresponding actual frequency, we need to know the corresponding sampling rate. So note that this is a normalized frequency. Let us now look at the problem. Consider two continuous time signals, x1t equal to cos 20 pi t and x2t equal to cos 100 pi t. If these signals are sampled at a rate 40 samples per second, what will be the corresponding discrete time signals? This is the first part of the problem. Let us look at this. So given signal x1t equal to cos 20 pi t or cos 2 pi f1t. Accordingly, f1 is equal to 10 hertz, and given the sampling rate fs as 40 samples per second, so the corresponding normalized frequency small f1 equal to capital F1 by fs, that is 10 by 40 or 1 by 4. So the corresponding discrete time signal x1n would be, so this implies x1n would be, as we just saw here, it takes the form a cos 2 pi fn lowercase fn. So it takes the form here cos 2 pi f1n, and f1 is 1 by 4. So cos 2 pi into 1 by 4 n, that is equal to cos pi by 2 n. So this is the corresponding discrete time signal that we obtain when we sample x1t equal to cos 20 pi t at a sampling rate of 40 samples per second. Now what happens when we sample another signal cos 100 pi t at the same sampling rate? Note that here the corresponding frequency would be 50 hertz, and we are sampling it at 40 samples per second, which is less than the Nyquist rate, and therefore it will result in aliasing, as we'll shortly see. So consider the second signal x2t equal to cos 100 pi t equal to cos 2 pi f2 t. By comparison, f2 is equal to 50 hertz, fs is given to be 40 samples per second. Therefore, the corresponding normalized frequency small f2, which is capital F2 upon fs, that is 50 by 40 or 5 by 4. Accordingly, the discrete time signal that we get x2n is equal to cos 2 pi fn equal to cos 2 pi into 5 by 4 n, or that is equal to cos 5 pi by 2 n. Now note that this cos 5 by 2 n can be written as cos 2 pi n plus pi n by 2, and cos 2 pi n plus theta is cos theta. So what we get is cos pi by 2 n. Interestingly, you see that both x1n and x2n are exactly same. Let us read the question further. If the discrete time signals are again converted to continuous time signals using ideal interpolation, what will be the corresponding continuous time signals, and which effect do you observe here? So, if you reconstruct the signal from the samples using ideal interpolation, what do you get? For the first signal from x1n, if you use ideal interpolation or sync interpolation, you get back x1t exactly, because in this case the sampling rate 40 samples per second was greater than the Nyquist rate, because the signal frequency in this case was 10 hertz. So the Nyquist rate for it would be 20 samples per second, and we are sampling at 40 samples per second. So we are sampling above the Nyquist rate, and therefore using ideal interpolation we get the signal back. So perfect reconstruction, because here we use the oversampling. However, when we look at x2n and use the ideal interpolation again, we don't get x2t back, rather we get x1t back. So we get x1t, which is not equal to x2t, of course, because x2t is cos 100 pi t, but our sampled signal is cos pi by 2n, which gives us back cos 20 pi t. And this non-ideal reconstruction, non-perfect reconstruction, is the result of undersampling. It is the effect of undersampling, that is sampling at a rate less than the Nyquist rate, and the effect manifests in the form of what we call aliasing. What is aliasing? Aliasing is the phenomenon in which some high frequency component takes on the identity of a low frequency component. As in this example, we saw that the 50 hertz signal, originally it was 50 hertz signal, it appears as a 10 hertz signal after reconstruction if the sampling is at a rate lower than the Nyquist rate. So just once again note that the original signal x1t was of the form cos 20 pi t with the frequency as 10 hertz, and the second signal x2t was of the form cos 100 pi t with signal frequency as 50 hertz. Now we see that when this signal was sampled at 40 samples per second, then after reconstruction this 50 hertz signal reappears as a 10 hertz signal, and this phenomenon is known as aliasing. This problem of aliasing could be overcome if the sampling rate is kept higher than the Nyquist rate. So I hope this problem must be clear to you all. Thank you.